Something fell into a black hole. A person, we will say, and now the black hole is gone. It finished evaporating. Every last scrap of it boiled away into a thin mist of radiation, spreading out into cold, empty space. And here's the problem. Whatever that person knew, whatever they were made of, the exact quantum arrangement of every particle in their body, that information should still exist somewhere. Physics is very clear on this point. Information cannot be created and it cannot be destroyed. It can be scrambled, it can be hidden, it can be spread across a trillion particles until no one could ever hope to read it again. But it cannot simply stop existing.
So where did it go?
Picture yourself as that person. You suit up, you get in the ship, and you cross the horizon of a black hole massive enough that you do not even feel it happen. No crushing force, no alarm bells. You just keep falling. And on the outside, decades pass. Then centuries. The black hole you fell into keeps radiating, keeps losing mass, shrinking in total silence until one day it lets out its last whisper of energy and disappears completely. Nothing is left where it used to be, just that faint hiss of radiation drifting outward, cooling, spreading through the dark. This is not really a story about black holes. Black holes are just where the crime scene happens to be. This is a story about whether the universe keeps a record of everything that has ever happened to it, or whether some things can just be erased, whether reality keeps its receipts. Prepare yourselves. We begin. Start with the picture general relativity gives you, because it is clean, and for a long time physicists thought it was the whole story. In 1916, a German physicist named Karl Schwarzschild was serving on the Eastern Front during the First World War. He was sick. He would die within the year. And in whatever time he had between artillery postings, he sat down with Einstein's newly published equations of general relativity and found the first exact solution anyone had ever produced for them. Not an approximation, not a rough sketch. An exact description of the space and time surrounding a single spherical mass, sitting alone in an otherwise empty universe. Einstein himself did not think anyone would solve his equations exactly. They were that hard. Schwarzschild did it from a trench. What his solution described is what we now call the Schwarzschild metric, and it is the starting point for almost everything you think you know about black holes. Picture a single number, the mass of some object, and imagine you shrink that entire mass down smaller and smaller, packing it into a tighter and tighter ball without losing a single gram of it. Nothing dramatic happens for a while, but cross one particular radius, a threshold now named after Schwarzschild himself, and the mathematics changes character entirely. Inside that radius, the equations say, nothing can ever climb back out. Not light, not information, not you. That boundary is the event horizon, and general relativity treats it as a strange kind of boundary indeed. If you were falling toward it, you would not feel a wall. You would not feel anything unusual at all, assuming the black hole is large enough that the stretching forces stay gentle. The horizon is not a physical surface. It is a point of no return written into the geometry itself, a place where the equations say escape becomes mathematically impossible, even though nothing local marks the spot. Mathematicians call this a coordinate singularity, and the name matters. It looks like infinity blows up right there in the equations, but that is a flaw in the coordinates you chose to describe the space, not a flaw in space itself. Switch to a better set of coordinates, and the horizon smooths out completely. You could cross it and never know, at least not from anything happening right where you are. The real singularity is a different animal entirely, and it sits at the center, not the edge. Here, according to classical general relativity, all of the black hole's mass gets crushed down into a single point of zero size and, on paper, infinite density. Space and time themselves stop making sense there. This is not a coordinate trick you can wash away by picking better math. Every serious physicist treats this as a sign that general relativity is telling you, quite honestly, that it has reached the edge of its own authority. The theory works beautifully everywhere else. At the singularity, it simply stops answering questions. And here is the part that made black holes feel so clean, so satisfying to physicists working through the middle of the 20th century. Whatever fell in, whatever star collapsed to form the thing, Whatever ship or person or planet crossed that horizon afterward, none of it left a trace on the outside. A black hole once formed can be described completely using exactly three numbers: its mass, its electric charge, and its spin.
Nothing else.
Physicists call this the no-hair theorem, because a black hole has no distinguishing features left, no fingerprints, no memory of its past, nothing sticking out that would let you tell one black hole from another beyond those three numbers. Two black holes with identical mass, charge, and spin are, according to this picture, absolutely indistinguishable, even if one formed from a collapsing star and the other from a pile of encyclopedias. In this classical picture, black holes are eternal. They do not radiate. They have no temperature, no glow, nothing leaking outward. They simply sit there, silent and permanent, swallowing anything that wanders too close and giving nothing back. Simple, immutable, and as it turns out, completely wrong about one crucial detail. Prepare yourselves. We begin. In 1974, a physicist sat down to do a calculation, not to overturn physics, not chasing anything about information or paradoxes. He simply wanted to know what quantum field theory actually predicts when you apply it to the curved space sitting right outside a black hole's event horizon. Nobody expected the answer to be interesting. Black holes were supposed to be simple: mass, charge, spin, the end of the story. Stephen Hawking ran the math anyway, and the result should not have been possible. To understand why, you need to know what empty space really is, according to quantum theory. And the truth is that empty space is never actually empty. At every point, all the time, everywhere in the universe, pairs of particles flicker into existence and vanish again almost as fast as they appear. A particle and its antiparticle partner, borrowed briefly from the vacuum, then paid back an instant later when they collide and annihilate each other. This is not a rare event. It is happening right now, in the space between you and your screen, constantly, and it cancels out so cleanly that you would never know. Now put that same flickering vacuum right next to an event horizon. Here is what Hawking found. Sometimes one of those two particles forms just barely on the inside of the horizon, and its partner forms just barely on the outside. Normally they meet back up, annihilate, debt repaid, nothing gained, but the horizon gets in the way. The infalling twin cannot climb back out to complete the pair.
Gone, swallowed.
Its partner, left with no one to annihilate with, has no choice but to become real. An actual particle streaming away from the black hole, out into the universe. If it happened once, it would be a curiosity, but it happens continuously forever, all along the horizon, and the result is a steady outward flow of particles that Hawking realized was indistinguishable from heat. Radiation, constant, measurable, draining away from the black hole in every direction. Now, here is the part that actually matters. Every particle that escapes carries energy. Energy the black hole had to supply, which means every particle that escapes costs the black hole a little bit of mass. Black holes are not eternal vaults after all. They leak. They lose weight, slowly, continuously, and given enough time, they shrink down to nothing and vanish. That alone rewired how physicists thought about black holes, but the second part of the discovery planted a bomb under the whole field. Hawking checked what kind of information this outgoing radiation actually carried. Not what fell in, not who it used to be, what it used to be made of, just its temperature. A single number determined only by the black hole's mass. No fingerprint, no signature, no trace of the star that collapsed to form it, or the astronaut who crossed the horizon centuries later. The radiation was perfectly, featurelessly thermal, which means if you let a black hole evaporate all the way down to nothing, all you're left with is heat, undifferentiated, faceless heat. But this was just the beginning. To understand why featureless heat is such a problem, you need to understand a word that physicists throw around constantly and rarely explain well: entropy. Forget disorder for a second. Forget the messy bedroom explanation you probably heard in school. At its core, entropy is a count, a measure of how many different hidden arrangements of a system would all look exactly the same from the outside. Take a room full of air. If every molecule is spread out evenly, bouncing around in a trillion different possible configurations, all of them look identical to you standing in the doorway. You just see a room with air in it. That is high entropy. Now cram those same molecules into one corner. Suddenly, there are far fewer ways to arrange them and still get all the air crammed in one corner. That is low entropy. Fewer hidden options, more hidden information about exactly where things sit. Here is why this matters for black holes. Years before Hawking sat down with his calculation, a physicist named Jacob Bekenstein looked at black holes and noticed something that should have been alarming. If a black hole can swallow anything, hot gas, cold gas, ordered matter, disordered matter, and just add it to its total mass with no other consequence, then you could take a box of high entropy gas, toss it in, and the universe's total entropy would appear to drop. The messy hidden information in that gas would simply disappear behind the horizon. No accounting for it anywhere. That is not allowed. The second law of thermodynamics is one of the strictest rules in all of physics. Entropy never decreases for the universe as a whole, not even a little, not even once. So Bekenstein reasoned that black holes had to carry entropy themselves, entropy that goes up whenever something falls in, keeping the universe's books balanced. Hawking's later discovery of radiation confirmed Bekenstein was right and gave the idea a precise number. But it is the shape of that number that should stop you in your tracks. Black hole entropy does not scale with the volume of the black hole. It scales with the area of its horizon, the flat, two-dimensional surface wrapped around the outside. Sit with that, because your intuition is screaming that this is backwards. More space inside, something should mean more room to hide information. A bigger box holds more secrets than a bigger sheet of paper. That is how information works everywhere else in your experience. Pack more stuff into more volume, and you can hide more. But a black hole does not care how much interior space it has. Double its radius, and its interior volume grows one way, but its capacity to hide information grows only with the area of its skin. It is as if the deepest truth about how much a black hole can conceal was never written into its depth at all, only into its surface. Physicists still argue about what to make of this. Some treat the area law as a screaming hint about the true, deeper structure of quantum gravity, a sign that space itself does not work the way we assume. Others suspect it might just be a strange accident of the classical math, a coincidence with no deeper meaning waiting underneath it. Nobody in 1973, watching Bekenstein defend this idea against skeptical colleagues, had any sense of where it was about to lead. So now you have two rules sitting in the same universe, and they cannot both survive contact with each other. General relativity declares the event horizon absolute. Nothing that crosses it returns, and nothing inside can ever influence the outside, except through those three numbers: mass, charge, and spin. That is not a suggestion. It is built into the geometry itself. Quantum mechanics, meanwhile, insists that information is never destroyed. Not even in principle, not even under the most extreme conditions physics can construct. Physicists call this rule unitarity, and it means something very specific. Take the exact quantum state of anything, run it forward through time using the laws of physics, and that evolution must be reversible. Rewind it, and you get back exactly what you started with. No blur, no loss, no rounding error. Every quantum interaction that has ever happened is, in principle, undoable. Consider an analogy that holds up under pressure. Take a book and burn it. Watch it turn to smoke, ash, and heat radiating off into the room. It looks gone. It looks like the information, every letter, every sentence, has been erased. But physics insists that is an illusion of scale, not a genuine loss. If you could track every single photon of light, every molecule of smoke, every vibrating atom of ash, with impossible precision, the information about the book's exact contents would still be sitting there, smeared out across all of it, scrambled beyond any practical hope of reading it back, but not gone. Recoverable, at least in principle, by something with perfect knowledge and perfect tools. That is what unitarity demands everywhere else in physics. And that is exactly what Hawking's calculations seem to remove from the table. Because remember what came out of that horizon. Not scrambled smoke carrying a hidden trace of the book. Pure, featureless heat. A temperature, and nothing else. If Hawking radiation really is exactly thermal, with no correlations, no fingerprint, no residual imprint of whatever fell in, then burning this particular book leaves behind ash that tells you literally nothing. Not difficult to read. Nothing. No amount of tracking every photon would help, because the information was never encoded in them to begin with. That is not scrambling. That is erasure. And erasure is the one outcome unitarity forbids, absolutely without exception. So something has to give. Either quantum mechanics is wrong about this one rule it treats as sacred, or general relativity's picture of the horizon, that clean absolute one-way door, is missing something. Two camps formed almost immediately, and neither one budged for years. One side said fine, let quantum mechanics bend. If gravity is powerful enough to make information genuinely vanish, maybe unitarity was never truly universal to begin with, just a rule that holds until you push physics somewhere extreme enough to break it. The other side said no. Unitarity is untouchable, which means the horizon itself, that supposedly airtight boundary, must be leaking in some way general relativity never anticipated. Somehow, some way, the details have to be getting out. Neither side had proof. Both sides had a version of physics they were not willing to give up. Here is where it gets uncomfortable. By the 1990s, this disagreement had a face. Two faces actually on one side of a bet, and a third on the other. Stephen Hawking and Kip Thorne shook hands with John Preskill in 1997 over a wager that sounds almost too tidy to be real physics. Hawking and Thorne took the position they had defended for years. Information really is destroyed when a black hole evaporates, full stop, and quantum mechanics is going to have to learn to live with that. Preskill took the other side. He bet that information comes back out, encoded somewhere in that radiation, however scrambled, however impossible to read in practice. The terms of the bet tell you everything about how physicists think. The loser had to hand over an encyclopedia from which information can be retrieved at will. Not a metaphor, an actual physical encyclopedia. Its pages full of retrievable facts, standing in for the exact question at the center of the paradox. Can you get the information back out, or can you not? Do not mistake this for a stunt or a joke between colleagues. Bets like this are how theoretical physicists stake their reputations when no experiment can referee the argument. Nobody could point a telescope at a black hole and settle this. So Hawking, Thorne, and Preskill did the next best thing. They staked their names on opposite conclusions, in public, in a field where being visibly wrong actually costs you something. The bet sat unresolved for 7 years. Then, in July of 2004, at a conference in Dublin, Hawking stood up in front of the community that had watched this argument play out for 3 decades and reversed himself.
Information is not lost, he told the room.
He walked over to Preskill and handed him an encyclopedia. It should have felt like a clean resolution. It did not, because the mechanism Hawking offered to explain how information escapes was strange, even by the standards of theoretical physics. He argued you had to sum over every possible shape spacetime could take, every topology, and that when you did the math this way, the version where information genuinely disappears simply does not dominate the final answer. Most of his colleagues nodded along, conceded the headline, and quietly stayed unconvinced by the specific argument underneath it. Getting from quantum mechanics wins to a working physical explanation of how a black hole actually returns information turned out to be two very different problems. Here is the part that is hard to shake once you notice it. The physicist whose name is permanently welded to the phrase information loss, the man who spent 30 years insisting black holes destroy information, spent the last decade of his life on the record saying the opposite. He called his original claim a mistake, and the deeper mechanism, the actual how, remained an open question that outlived him. The black hole information paradox never stayed confined to black holes. That is where it began, but it could not remain there. The implications were too large. If information can genuinely be destroyed, not scrambled, not hidden, but actually erased from existence, then you have opened a door that does not close again. The same rule that would let a black hole erase the details of what fell into it would apply everywhere else too. The same physical state sitting right in front of you could in principle have two completely different pasts, two different histories that both collapse into the identical present moment with no way, even theoretically, to tell which one actually happened. Consider the chain of what that implies. It does not stop at black holes. What if determinism itself only looks solid because we have never pushed physics hard enough to find its edges? What if causality, the assumption that a cause has to precede its effect in some consistent, trackable way, only holds most of the time in most conditions and simply gives out under strong enough gravity? What if the future is not actually fixed by the past, the way every equation in physics assumes it is, and what looks like a hard law is really just a pattern that happens to hold everywhere we have thought to check? That is the real fear underneath this paradox, and it deserves to be stated plainly instead of dressed up. Quantum mechanics is not just one more theory about how particles behave sitting on a shelf next to the others. It is the operating system. Every other theory in physics chemistry, every model of how atoms bond or stars burn or electrons move through a wire, all of it runs on the assumption that quantum evolution is unitary, that information is conserved, that the universe never quietly deletes anything. Pull that assumption out, and you are not just revising black hole physics. You are threatening the foundation everything else was built on top of. That was what was actually at stake for the physicists who debated this for 30 years, and it is worth being honest about why they cared so much. Their entire framework for predicting anything, from the decay of a radioactive atom to the outcome of a particle collision, depends on this one rule holding everywhere, always, with no exceptions carved out for extreme gravity. If black holes get an exception, you have to ask what else might. Maybe nothing else does, but nobody gets to just assume that. You have to prove it, and for a long time nobody could. So where does the fear actually sit today, now that the field has had decades to work through it? Most physicists have landed in the same place. Information survives, unitarity holds. Black holes do not secretly delete the universe's records. That much, as we saw with Hawking's own reversal, has become close to a consensus position. But landing on an answer and understanding the mechanism behind it are two different achievements, and only one of them has actually happened. Physicists can tell you with real confidence that the books balance in the end. What almost none of them can tell you with the same confidence is exactly how the universe pulls it off. That gap between knowing the answer and understanding the method is exactly what the next 60 years of this story is about. Now meet the physicist who refused to let the area law sit quietly in a corner. Gerard Hooft had already won a Nobel Prize by the time he found himself staring at Bekenstein and Hawking's strange result. He decided it could not be just a footnote. Most of his colleagues treated the area law as a curious detail of black hole thermodynamics, an oddity to note and move past. Hooft looked at it and asked a much bigger question. If a black hole's entropy scales with its surface instead of its interior, what if that is not a special rule for collapsed stars at all? What if it is a rule about space itself? Here is the leap he made, and it is worth walking through slowly because it is the hinge the rest of this story turns on. A black hole's horizon caps how much information can hide inside it, and that cap is set by area, not volume. Hooft asked, why would that be true only for black holes? Draw a boundary around any region of space you like, a room, a planet, a galaxy, and ask the same question, how much information could possibly be packed inside? If the black hole case is a hint about the deep architecture of quantum gravity rather than an accident of collapsed stars, then the answer for any region should follow the same rule. The maximum information is not set by how much three-dimensional space you have got to work with. It is set by the two-dimensional surface wrapped around the outside of it. Picture the boundary of any region as a kind of screen, not a screen in the sense of a TV, but in the sense of a projector surface, something that holds a complete record of everything happening inside. Everything you would ever want to know about the interior, in this picture, is already written on that outer surface, and the interior itself is something closer to a readout, a display running off of data that technically lives somewhere else. Say that plainly because it deserves to be said plainly. If Hooft is right, the three dimensions you're sitting in right now, depth, height, width, the full sense of room around you, might not be the place where reality actually keeps its books. They might be more like the picture on the screen, generated from information stored one dimension down. That is about as large a claim as physics gets, and it landed almost exactly nowhere in 1993. Most physicists reading T. Hooft's paper treated it as an interesting thought experiment, worth a footnote in a seminar. not a serious proposal about how the universe is actually built. Quantum gravity was already a graveyard of promising ideas that fizzled under scrutiny, and an argument this strange, this untestable, easy to wave off as speculation dressed up in Nobel laureate credibility. Hooft had the reputation to get people to read it. He did not yet have the argument that would make them believe it. The area law was not just a curiosity, it was a clue. Hooft treated it as one, but the rest of the field was not ready to follow. That argument was about to come from someone else entirely. Prepare yourselves. We begin. That someone was Leonard Susskind, and what he did with T. Hooft's idea was turn a strange conjecture into something you could actually build a physics career on. Susskind read the same area law, saw the same implication, and instead of leaving it as a philosophical aside, he started asking how you would make it rigorous. If the universe really does keep its books on a boundary, instead of in the volume, there has to be some fundamental unit to that bookkeeping, some smallest possible chunk of information. The way a dollar is made of cents. Susskind proposed exactly that. One bit of information for every Planck area of that boundary. The Planck length is about as small as distance gets before the concept of distance itself stops making sense, and a Planck area is that length squared. Carve up any boundary into patches that size, and each patch gets to store exactly one bit, no more, no less. That is the whole ledger, and nothing about the physics inside the region can exceed what that ledger allows. Picture this. Consider a credit card, the kind with a small holographic sticker on it. Tilt it back and forth, and you see a three-dimensional image shift and move, full depth, full perspective, changing as your angle changes. All of that visual information, every angle you could view it from, is stored flat, on a thin two-dimensional film pressed onto plastic. The image looks like it has depth. The storage medium does not. Susskind claimed that our universe might work the same way, except the sticker is the boundary of a region of space, and the image is everything happening inside it, including you. But be precise here. This is the exact point where people usually run the idea off the rails. Susskind was not saying the world is fake, or that matter is somehow an illusion you should stop trusting. He was saying something much narrower and much stranger, that the deepest layer of bookkeeping, the actual accounting of how much can happen in a given region, might live one dimension down from where we experience it. The three-dimensional room you're sitting in is completely real. It is just possibly not where the fundamental data lives. And once you accept that much, the reframe gets uncomfortable fast. Matter, gravity, the very sensation of depth you have looking around this room right now, none of that has to be a foundation. All of it could be the shadow cast by information encoded somewhere else entirely, on some boundary you will never see, never touch, never point a telescope at directly. You would be living inside the projection and mistaking it for the source. Susskind titled his paper on this, "The World as a Hologram," and the title was not decoration. It was the argument. What 2 Hooft had sketched as a possibility, Susskind sharpened into a framework with actual rules, actual units, actual math you could push on. It still needed something the whole community could point to and say, "Here, this is proof, not speculation." That proof was still 3 years away, and it was going to come from a place nobody expected. A young physicist working through equations in string theory, not looking for anything like this at all. But that was just the beginning. What comes next reveals something even stranger. The boundary keeps the books, but what happens when you try to cheat the ledger? Run the thought experiment all the way through. Take some region of space, seal it off in your imagination, and start stuffing information into it. More particles, more detail, more distinct configurations packed into the same volume. For a while, nothing strange happens. You are just filling a room, but the holographic bound says there is a hard ceiling here, set by the area of the boundary wrapped around that region, and the closer you get to that ceiling, the stranger your options become. Here is what actually happens when you push past it. The region does not become more informative. It becomes a black hole. That is not a metaphor, and it is not a coincidence either. Cram enough mass and energy into a fixed volume, and gravity stops being polite about it. Once you exceed the density the boundary can support, the region collapses under its own weight, and an event horizon forms right where your boundary used to be. You did not get a denser room. You got a trapdoor. The universe's answer to "can I store more than the boundary allows" is always the same answer: no, and here is a black hole to prove it. Consider what this means for something as ordinary as density. There is a version of this idea that gets tossed around to make the scale concrete. If you compress the Earth down to the size of a marble, you would not have a very dense marble sitting on a table.
You would have a black hole, because you would have blown straight through the threshold where geometry itself takes over.
Physical density is not an open-ended dial you can keep turning. It has a ceiling built directly into the shape of space, and the ceiling is the horizon. Now stretch this past black holes entirely, because that is the part that actually matters here. If any region of space obeys this same bound, then the observable universe itself, the whole thing, everything you could, in principle, ever see or interact with, has a maximum information capacity, not an estimate, not a rough guess, a number fixed by the area of the cosmic boundary that, in principle, you could actually calculate. Every particle, every field, every possible arrangement of matter within the reach of your telescopes, all of it capped by a single figure tied to the size of the observable universe's edge. Let that sink in. The universe is not just big. It is finite in a very specific, countable sense, not in how much space it has, but in how much it is allowed to know about itself. But here is where it gets uncomfortable. This argument holds up cleanly in idealized cases, tidy regions with well-defined boundaries, the kind physicists can actually do math on. Whether it generalizes cleanly to messy, real, expanding cosmological regions with all their complications is genuinely still contested. Skeptics want a tighter derivation before they will call this settled physics rather than a suggestive extrapolation. Nobody has proven the bound has to hold everywhere reality gets complicated. It is a limit that looks universal from where we are standing, but looks universal and is proven universal are two very different claims. And this is a field that has learned the hard way to keep those separate. That young physicist was Juan Maldacena, and in 1997 he was not hunting for a theory of everything. He was working through the equations of string theory, chasing a technical question about a particular class of objects called brains, and he found something that had no business showing up in the middle of that calculation. To see why it mattered, picture two universes side by side, because that is genuinely what Maldacena was comparing. On one side, take a universe built out of anti-de Sitter space, a curved, saddle-shaped geometry where gravity behaves exactly the way general relativity says it should. Stars form, black holes collapse, light bends around massive objects, all the ordinary physics you would expect from a universe with gravity in it. This space has a strange property. If you tried to walk toward its edge, you would never actually hit a wall. The geometry stretches out ahead of you forever. So the boundary sits at what is technically an infinite distance away, even though it still wraps the whole space like a container. Physicists call the interior of that container the bulk. Now take the other side. Living exactly on that boundary, one dimension down from the bulk, is something completely different. A conformal field theory, a flat, ordinary quantum system with particles and fields interacting according to quantum rules. No gravity anywhere in it. No curved space. No black holes, no horizons, just particles pushing on particles, the same basic kind of physics used to describe things like light and electrons, except confined to a lower dimensional surface. Here is what Maldacena found when he worked out how these two systems relate to each other. They are not just similar. They are not just connected by some rough approximation. Every question you could ask about physics in the curved gravity-filled bulk has an exact answer in the flat. Gravity-free boundary theory, and the two answers always match, every single time. Ask about the temperature of a black hole in the bulk, and the boundary theory gives you back the exact same number, computed with zero gravity anywhere in its equations. These are two totally different descriptions, built from completely different ingredients, and they describe the identical physical reality. Consider a video game cartridge. On the screen, you get sprawling, rich three-dimensional worlds. Mountains you can climb, physics you can feel, an entire universe with depth and weight to it. But none of that exists as depth on the cartridge itself. What is actually stored there is a long sequence of code, flat data with no spatial thickness to it at all. Nobody would say the game world on the screen is fake. It is just that. Its complete description, its actual storage lives in a different form. one dimension removed from what you're looking at. That is the relationship Maldacena had uncovered between the bulk and the boundary, except now it was not a metaphor. It was an equation. And here is where the shock actually lands, because it is easy to read past this too quickly. The boundary theory has no gravity built into it anywhere. None. And yet it reproduces every gravitational effect happening in the bulk, perfectly, without exception. Which means gravity in this framework is not a separate ingredient added on top of some more basic physics. Gravity is what a gravity-free quantum system looks like from the inside. Once you are standing in the bulk, it is projecting. So sit with the question this actually raises, because it is not a rhetorical flourish. It is the question that genuinely stopped physicists in seminar rooms. If a theory with zero gravity in its equations reproduces gravity's effects exactly, every time, with no exceptions, does gravity actually exist? Or have physicists spent a century studying the shadow of something else and mistaking it for the main event? The honest answer is not yes, and it is not no, and it is worth resisting the urge to flatten it into either one. Gravity is real.
You can measure it.
Drop something and it falls every time. And general relativity predicts exactly how it falls with a precision that has been checked over and over. That is not in question. What is in question is whether gravity belongs on the list of things. Physics calls fundamental the bedrock ingredients everything else is built from, or whether it belongs on a different list entirely, things that are completely real but only show up once you have got enough of something else piled together. Here is a comparison that actually holds up. Waves on the ocean are real. You can surf one. It can knock you over, and it can carry a ship for miles. But a wave is not a separate substance poured into the water. There is no wave stuff mixed in with the water molecules. A wave is what water molecules do when enough of them push against each other under the right conditions. Zoom into a single molecule and there is no wave there at all, just a particle bumping into its neighbors. The wave only exists once you step back and look at the whole crowd of them moving together. Gravity in Maldacena's framework might work the same way. Curved space-time, the bending and warping that general relativity describes so beautifully, might be the wave, and the boundary theory, that flat, gravity-free swarm of quantum particles interacting according to ordinary rules, might be the water. Zoom into the boundary theory's actual ingredients, and you will not find anything labeled gravity anywhere in there. No curvature, no bending of space, none of it. But step back, look at the whole system doing what it does, and gravity in the bulk falls out of it anyway. The exact same way a wave falls out of water that has no wave built into its molecules. That reframe is enormous because it means the thing physicists have been trying to unify with quantum mechanics for the better part of a century, the thing that resisted every attempt to fold it into the same mathematical language as everything else, might never have needed unifying in the first place. It was never a separate force sitting stubbornly apart from quantum theory. It might just be what quantum theory looks like once you're standing inside the world it is projecting. Not every physicist finds this equally convincing, and it is worth saying plainly where the disagreement actually sits. Some researchers treat this as close to settled, the natural and almost inevitable reading of everything Maldacena's correspondence has produced since 1997. Others are far more careful, and they have got a real point. This picture has been proven rigorously in one very specific kind of universe, the saddle-shaped anti-de Sitter kind, and our universe does not look like that. Whether the same logic holds anywhere else, including here, is a separate question entirely, and it is one nobody has closed the book on yet. Go back to whatever physics class first taught you how the universe holds itself together, and you got some version of the same list. 4 fundamental forces. The strong force gluing the nucleus shut, the weak force responsible for certain radioactive decay electromagnetism running everything from light to your phone battery, and gravity tagging along at the end, always treated as an equal member of the same club. 4 basic ingredients, each one fundamental, each one irreducible, each one as bedrock as the others. Here is what Maldacena's correspondence quietly does to that list. It does not add a 5th force or rearrange the order. It knocks gravity clean off the page. If curved spacetime really is the emergent byproduct of some deeper quantum system, the wave produced by the ocean rather than an ingredient poured into it, then gravity was never a fundamental force to begin with. It is a macroscopic side effect, something that shows up once you have enough of the boundary theory's actual ingredients working together, but nothing you would find if you dug down to the bottom layer looking for it directly. The other three forces belong on that foundational list. Gravity is just what happens once the list is fully assembled and running. You can watch this play out concretely in the decades-long hunt for the graviton. Physics already has a clear pattern for how forces work at the most basic level: a carrier particle. The photon carries the electromagnetic force, gluons carry the strong force, and physicists spent years building the theoretical case for a graviton, a particle that would carry gravity the same way, assuming gravity had to fit the same mold as everything else on that list. But if gravity is emergent, that hunt was never going to succeed, not because the particle is hard to detect, but because there may be nothing there to find. You cannot locate the carrier particle for a force that was never fundamental in the first place. Asking where is the graviton becomes a bit like asking which water molecule is carrying the wave. The wave is real, but it is not a thing any single molecule is holding onto. What this does is reframe one of the largest ambitions in modern physics. For most of the last century, the goal was to find quantum gravity, a theory that would take Einstein's smooth geometric picture of curved spacetime and somehow force it into the same mathematical language as quantum mechanics. The language that already works beautifully for the other three forces. Decades of effort, and no fully satisfying version of that theory ever quite came together. Maldaceno's result points to a reason why, and it is a strange kind of relief buried inside a strange kind of demotion. Quantum gravity may not need its own separate theory at all, standing apart from ordinary quantum mechanics, waiting to be discovered, because it was never a separate thing to unify in the first place. Once you understand the boundary theory well enough, gravity in the bulk falls out of it automatically, the same way heat falls out of jostling molecules without needing its own extra rulebook bolted on top. The unification physicists spent a century chasing might already be sitting inside a theory that never mentioned gravity at all. Before you go any further into this, you need to reset the foundation, because the next few chapters of this investigation rest on something most people have heard of, but very few actually understand: entanglement. Here is the plain version, stripped of the mysticism that usually gets bolted onto it. Two particles can be produced in a way that ties their properties together so tightly that measuring one instantly tells you something exact about the other, no matter how far apart they have drifted since. Not probably tells you or gives you a decent guess, instantly and exactly, every single time you check. Picture two coins that have been linked at the moment they were flipped, so that whatever one lands on, the other is guaranteed to land on the opposite face. Separate them, sending one to the far side of a room, the other across a city, across a planet. It does not matter. Flip them at the same instant, and the moment you look at one and see heads, you know, with total certainty, that the other one came up tails. You did not send it a signal or touch it. The correlation was baked in from the start, and distance never loosens it. That description undersells how strange this actually is in real quantum systems, because unlike ordinary coins, the entangled particles do not have a fixed outcome until one of them gets measured. Both possibilities sit in superposition, both real at once, right up until the instant of measurement collapses one side of the pair, and the other side snaps into agreement immediately, regardless of distance. Einstein hated this, spending decades calling it spooky action at a distance, and he meant that as an insult, not a compliment. To him, it looked like a flaw in quantum mechanics, a sign the theory was incomplete, because nothing in his universe was supposed to coordinate itself across space without some signal traveling between the 2 points to explain it. For years, most of the field treated entanglement the same way, a strange side effect of quantum math, uncomfortable, slightly embarrassing, something you worked around, rather than something you built anything out of. It got explained in textbooks, tested in labs, confirmed again and again, yet still got treated like a curiosity, a weird property particles happen to have, not a tool for constructing anything larger. That treatment did not last, because somewhere along the way, a shift happened in how physicists thought about what entanglement was. It stopped looking like a side effect and started looking like a raw material, not something that merely happens between particles sitting inside space, but something that might be doing actual construction work, laying down the very fabric those particles sit inside of. The correlation itself in this new picture is not decoration on top of geometry, but might be the thing geometry is made from. Here is the claim waiting at the end of that shift, and it is worth stating plainly before we walk through how anyone arrived at it. Some physicists now think entanglement is not just something that occurs in space. They think it is what builds space in the first place. Strip the entanglement out of a system, and you do not just weaken the space connecting its parts, you lose the connection entirely. Distance itself on this view might be nothing more than a measurement of how little two things are tied together. That is the thread the next part of this investigation has to pull on directly. Prepare yourselves. We begin with a thought experiment that forced physicists to take that claim seriously. It belongs to a physicist named Mark van Ramsdonk. Start with one of Mulder-Seiner's boundary systems, the flat, gravity-free quantum theory, living on the edge of an anti-de Sitter universe, and split it conceptually into two halves. In their normal state, these halves are entangled with each other, tied together the way any two pieces of a single quantum system tend to be. On the bulk side, the gravitational universe that boundary projects, this entangled boundary corresponds to one single connected spacetime.
One universe in one piece.
Now run the experiment. Dial down the entanglement between those two boundary halves, not erasing particles, not removing any energy, just loosening the correlation between them, bit by bit. Watch what happens on the bulk side while you do it. The connected spacetime does not get thinner. It does not stretch or weaken evenly, the way you might expect if space were some kind of elastic material losing tension. It tears. As the entanglement drops, the geometry connecting the two regions starts to pinch. Keep going, stripping entanglement all the way down towards zero, and the bulk spacetime does not end up as one weak, barely connected universe. It splits cleanly into two separate universes, completely disconnected from each other, with no path between them at all. Picture pulling threads out of a blanket. For a while, the blanket holds together fine, maybe a little thinner in one spot. But threads are not distributed one at a time evenly across the whole thing forever. Past a certain point, the fabric does not just get flimsy. It comes apart into two separate pieces, and there is no gradual middle state where you have half a connection holding the two halves loosely together. You have fabric, or you have two scraps of fabric. That is what Van Ramsdonk found in the geometry. Entanglement was not sitting quietly next to the connection between these two regions of spacetime. It was the connection. Remove it, and you do not get weaker space. You get no space between them at all. Here is the radical part, and it deserves stating plainly. If stripping entanglement all the way to zero severs a spacetime into two disconnected universes, then the reverse has to be true as well. Distance itself, the very thing separating any 2 points in space, might just be a way of measuring how little those 2 points are entangled. 2 points heavily entangled sit close together, loosen that entanglement, and they drift apart, not because anything physically moved, but because the correlation holding them near each other in the geometry has weakened. Push entanglement to zero, and they are not just far apart anymore. They are not in the same universe. That is an enormous claim to build on a thought experiment, and it is worth being honest about where it currently stands. This result comes from simplified, idealized models, the tidy anti-de Sitter playground where the math is tractable and the boundary theory is well understood. Nobody has shown rigorously that this is literally how distance works in the messy, expanding, matter-filled universe you are sitting in right now. It is a result about a toy universe that behaves suspiciously, like a clue about the real one. Whether that clue generalizes is exactly the kind of question the next stretch of this investigation has to sit with. Beneath everything you just heard about entanglement tearing space apart lies a deeper layer, and it belongs to a mathematician named John von Neumann. He worked out the quantum version of entropy decades before anyone thought to connect it to spacetime geometry. Every entropy definition that came before his, the spread of gas molecules, the hidden arrangements behind a system's outward appearance, all of it turns out to be a special case of something more basic. Von Neumann entropy is the deepest version, the one that applies once you stop pretending the world is classical and start taking quantum mechanics seriously as the actual bottom layer. Here is where it gets uncomfortable fast, so walk through it carefully with a single quantum coin. flip it, and it does not land on heads or tails the way a normal coin does. It enters a superposition, both outcomes existing at once, 50% heads and 50% tails, right up until somebody looks. And here is the strange part. That coin, sitting there unrevealed, actually has zero hidden entropy. None. Because its entire state is completely described by that superposition itself. You know exactly what it is doing, even though you do not know which way it will land. There is no missing information tucked away somewhere, no gap between what the coin is and what you know about it. Looking at it does not hand you new information about some prior hidden state. It just forces the superposition to pick a side randomly. Now, bring in a second coin entangled with the first, so that whichever way one lands, the other is guaranteed to land opposite. Consider the whole pair together, and the entropy is still zero for the same reason as before. The combined system's wave function fully describes everything happening between the two coins. Nothing hidden, nothing missing. But here is the moment everything changes. Stop looking at the pair, and look at just one coin alone, ignoring its partner entirely. That single coin, considered by itself, now has entropy that is not zero anymore. Real, measurable, non-zero entropy. Because part of that coin's story does not live in the coin. It lives in its partner, somewhere else entirely. If you're only looking at one half of an entangled system, you have lost access to information that is genuinely there, just not there in front of you. That is the insight worth sitting with, stated as plainly as it deserves. Entanglement is precisely what hides information from a partial view of a system. It is not that the information vanished. It is that you are only holding one half of a wave function that needs both halves to be complete. Von Neumann's entropy is exactly the tool that measures how much you are missing by only looking at your half. This is also how the classical world you actually experience emerges out of the quantum weirdness underneath it. Every object you touch is constantly entangling with the countless particles around it. Air molecules, photons, the table it is resting on. And as that web of entanglement spreads, it becomes practically impossible to ever access the whole picture again. That process is called decoherence, and it is why you never see a chair in superposition, heads and tails at once. The chair's quantum details are still there, technically just scattered into partnerships with everything nearby, permanently out of reach from any partial vantage point you could occupy. And this connects to something that reaches even further than the emergence of ordinary objects. As entanglement spreads across the universe, tying more and more of it together in ways no partial observer can ever fully see, that spread may be exactly what drives entropy's steady climb everywhere, in every system, at every scale. Which means the growth of entanglement itself might be the actual engine behind the arrow of time, the reason the past looks so different from the future at all. Take everything you heard about entanglement and time and aim it straight at a black hole. That is where this dictionary was built in the first place. Remember the bulk and the boundary? A curved gravity-filled universe on one side. A flat, gravity-free quantum system living one dimension down on the other. Every question in one translates exactly into the other. Apply that translation to a black hole sitting in the bulk, and here is what the boundary side gives back. Not a monster, not a singularity, not some exotic gravitational object at all.
You get a hot thermal state.
A system with a temperature, that is the whole translation. Let that sink in. What does hot state actually mean once you strip gravity out entirely? Nothing exotic. Just a swarm of ordinary quantum particles, jostling against each other, exchanging energy, settling into the same kind of thermal equilibrium you would expect from gas molecules bouncing around inside a sealed container. No horizons in this description, no warped geometry, no point of no return. Nothing that looks remotely like the object swallowing light on the bulk side. Just particles, doing what particles do at a given temperature, following rules with zero gravity, written into them anywhere. Here is a way to hold both pictures in your mind at once. Watch a packed stadium do the wave. From a distance, you see one continuous ripple moving around the bowl, rising and falling. Something that looks like a single coherent object traveling through the crowd. But there is no person who is the wave. Every individual in that stadium is just standing up and sitting down at roughly the right moment. The wave itself only exists as a pattern, that emerges once you stop looking at any one person and start looking at all of them together. Ask which specific fan is carrying the wave forward, and the question does not even make sense. The wave is real, it just is not located in any single seat. That is the relationship between the black hole in the bulk and the thermal soup on the boundary. Nobody looking at the boundary theory's actual ingredients would ever point to a specific particle and say, there, that is the event horizon. The horizon is not hiding somewhere in the boundary math waiting to be found. It is what the whole jostling crowd of particles looks like once you step back far enough to see the pattern they are collectively producing. State the payoff directly. Everything that reads as a mysterious gravitational object in one description, event horizon, singularity, boundary nothing escapes from, is just quantum particles in a hot soup in the other description. Same physics, translated into a language with no gravity, no curvature, no exotic geometry anywhere in it. Just particles at a temperature, doing exactly what particles at a temperature do. Here is where this lands for the entire information question you have been sitting with since the opening chapters. Ordinary quantum systems, swarms of particles at a temperature, do not destroy information. They can scramble it beyond any hope of practical recovery, spread it so thin across so many interactions that no experiment you could ever run would reconstruct it. But the underlying quantum evolution stays unitary the whole time, every detail preserved somewhere in principle. If a black hole really is nothing more than a thermal quantum system wearing a gravitational costume, then in principle nothing about it should be able to actually vanish. Whatever fell in has to still be sitting there, encoded somewhere in the boundary's jostling crowd, however impossible it might be to read back out. Here is a slogan that sounds like a typo the first time you read it. ER equals EPR, two sets of initials from two completely different papers, written by the same person in the same year, 1935. For 80 years, nobody thought they had anything to do with each other. Stands for Einstein-Rosen. A bridge, what most people call a wormhole. EPR stands for Einstein-Podolsky-Rosen, the paper that first described entanglement in the form Einstein hated so much he called it spooky. Two papers, same author, same year. One about the geometry of space bending back on itself, the other about particles correlated across a distance. Nobody, including Einstein, thought they were related. They were about different objects. One was gravity. One was quantum mechanics. Those did not talk to each other in 1935, and they mostly still do not, except here. Take each piece on its own first. A wormhole in the Einstein-Rosen sense is a geometric shortcut, a bridge connecting two points in spacetime that might otherwise sit unimaginably far apart, stitched together through some throat of curved geometry rather than through the ordinary distance between them. Entanglement, as you already know from the last several chapters, is a correlation between two particles so complete that measuring one tells you the state of the other. No signal required, no distance limit respected. The proposal put forward decades later by Maldacena and Susskind working together is that these are not two different phenomena that happen to share an author. They are the same phenomenon described twice. Every pair of entangled particles on this view is connected by a wormhole, not a large one, not one you could see or measure directly or send anything through, an impossibly thin, non-traversable bridge, but a genuine geometric connection all the same. Sitting underneath the correlation, the way Van Ramsdonk's tearing spacetime sat underneath his boundary theory's entanglement. Picture a thread strung between 2 points, not a tunnel wide enough to walk through, nothing you could climb into and come out the other side of, but a real physical connection joining them regardless. That is closer to what these wormholes are supposed to be. Not a corridor, a stitch. Here is why this reframes everything you have been sitting with since the opening chapters. If entanglement really is geometry, if the correlation between two particles is literally a thread of spacetime joining them, rather than some separate quantum add-on layered on top of space, then the black hole information problem was never really a question about information at all. It was a question about the shape of space itself. The Hawking radiation streaming away from an evaporating black hole is entangled with what is left behind. If that entanglement is geometric, then so is the connection between the radiation and the black hole's interior. The paradox stops being where did the information go and becomes, what does the geometry connecting inside and outside actually look like once you take entanglement seriously as a structural feature of spacetime? Be exact about where this stands. The slogan is catchy enough that it is easy to overstate. ER equals EPR remains a conjecture, explored mathematically in specific controlled models where the wormholes and the entanglement can both be tracked precisely. Nobody has confirmed this is literally how space-time works in our universe, with its real stars and real collapsing cores. It is a proposal that two things physicists have studied separately for 80 years might secretly be one thing. Whether that unification holds outside the models where it has been checked is still an open question, and it is about to matter enormously for the specific prediction this investigation has been building toward the whole time. Before wormholes, before islands, before boundary theories gave physicists a new language, there was Don Page. He asked a question that seemed almost too simple. If information truly survives a black hole's evaporation, what shape should the numbers take? Not a philosophical shape, a mathematical one. What curve would entropy follow if unitarity holds from start to finish? He worked this out in the 1990s. The answer was a curve with a very specific personality. Picture it forming in your mind. At the start, when the black hole first begins radiating, the entropy of the outgoing Hawking radiation climbs. That part matches Hawking's own math exactly. No surprise yet. Each new photon that escapes looks random, carries no obvious fingerprint of what fell in, and adds to the pile of apparent disorder streaming outward. The entropy rises, and for a while, this curve looks exactly like the one Hawking calculated back in the 1970s. But Page's version refuses to climb forever. It rises until it hits a peak, roughly at the halfway mark of the evaporation, a moment now named after him, the Page time. And then, if information is actually escaping rather than vanishing, the curve has to turn around. It has to fall. By the time the black hole finishes evaporating completely, the entropy of the radiation must come back down, approaching zero, because a fully evaporated black hole with nothing left behind should leave radiation that, considered as a whole, is back in a pure state. All the way up, then all the way back down. A curve shaped like a mountain, not a ramp. But here is where it gets uncomfortable. The falling half should have been impossible. Hawking's original calculation, the one built directly from quantum field theory on a fixed curved background, only ever produces the rising half. Nothing in that math ever turns the corner. You get a curve that climbs and keeps climbing, entropy piling up with no mechanism to bring it back down, right up until the black hole disappears entirely and leaves you with nothing that resembles a return to purity. Just an ever-growing pile of apparent disorder that never resolves. If you trusted that calculation completely, information loss was not just plausible. It was the only answer the math would give you. The stakes could not have been cleaner. Reproduce the falling half of Page's curve using an actual rigorous calculation rather than a hopeful argument, and you would have shown, mathematically, that information really does escape a black hole. Not as a philosophical stance, not as a matter of which camp you belong to in the bet between Hawking, Thorne, and Preskill. An actual number, falling the way it had to fall, produced by equations you could check. For decades, nobody could produce that number. The Page curve sat there as a target, a specific, falsifiable thing any serious candidate solution to the information paradox needed to reproduce, and calculation after calculation kept failing to hit it. You could talk about holography. You could talk about ads, CFT. You could talk about entanglement building spacetime. And all of it was suggestive. All of it pointed in the direction of information surviving. But suggestive is not the same as showing your work. The specific shape Page had derived, rise then fall, remained an unconfirmed requirement, a demand nobody had actually satisfied for very nearly 50 years after Hawking first calculated that black holes radiate at all. That gap between the theoretical demand and the mathematical proof is exactly where the next real breakthrough had to land. In 2019, that gap closed, not once but twice, from two directions that were not expected to converge. Two teams of physicists, working independently without coordinating, found the same missing piece within months of each other. One team included Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield. The other included Jeff Pennington, approaching the problem from a slightly different angle. Neither group set out chasing a headline. They were pursuing a technical gap in how entropy gets calculated near a horizon, and both landed on the same fix. The fix had a name nobody outside theoretical physics had heard before: quantum extremal surfaces. The idea itself is simple. Every calculation of entropy up to this point, including Hawking's original one, had been counting one kind of contribution only: the entropy carried by the radiation itself, streaming away from the black hole. What quantum extremal surfaces added was a second contribution, a gravitational one, coming from the geometry of spacetime itself near the horizon. Nobody had been including it, not because they had made an error, because nobody had realized it belonged in the sum at all. A term was missing from an equation everyone had assumed was complete. Once you know to look for that gravitational contribution, a stranger piece emerges from the same math, the island formula. Certain regions, technically sitting inside the black hole, past the horizon, in territory that should belong entirely to the interior, have to be counted as part of the outside radiation's entropy instead, not connected to the outside by any conventional path, just mathematically required to be counted alongside it. An island of interior geometry that behaves for this calculation as if it belongs to the exterior. Run the numbers with these islands included, and the result is extraordinary. The entropy calculation, which for nearly 50 years had only ever climbed, finally bends. It rises early on, exactly the way Hawking's math always said it would. And then, once you cross the halfway point, once an island appears in the geometry and starts contributing, the curve turns over and falls. It reproduces Page's curve, not approximately, not in spirit. The actual shape, rise then fall, appearing out of a calculation nobody could complete for 5 decades. Consider the implications for those who had spent years on this problem. The old calculations were not wrong in the sense of containing an arithmetic mistake. They were incomplete, missing a piece nobody knew belonged there. The way a ruler slightly too short will never measure a room correctly, no matter how carefully you use it. Every measurement taken with it comes back off by exactly the same margin, and the fix is not better arithmetic. It is a longer ruler. Islands were the longer ruler. Once physicists had the right tool in hand, the numbers that had refused to cooperate for 50 years simply worked. This matters, not as a footnote, as a resolution. For the first time, a mathematically controlled calculation, checkable line by line, using established tools rather than hopeful argument, showed that information can escape an evaporating black hole without breaking a single known law of physics. Not a conjecture, not a slogan, a computation with a curve at the end of it that rises and then falls exactly where Page said it had to. The paradox that opened this entire investigation, the one that had physicists divided into camps and placing bets over encyclopedias, had just produced its first real mathematical resolution. But resolving the numbers and understanding what they actually describe turned out to be two very different problems. Beneath these islands, the geometry of space-time takes a shape that reveals itself only when you stop treating the equation as a line and start asking what physical structure would produce it. When physicists trace out what the island formula requires, space-time itself develops something that looks exactly like a wormhole, a connection stitching the black hole's interior directly to the radiation sitting outside it, far from the horizon. Not a metaphorical link, a literal feature of the geometry these calculations are built on, threading through the mathematics, the same way a real bridge would thread through real space. This does not mean you could climb into this connection. No spaceship could enter the black hole's interior, ride this geometric feature, and pop out somewhere in the cloud of Hawking radiation drifting away. These are computational features, structures that show up when you extremize the right formula, not corridors carved through space that anything could physically travel down. The wormhole is not a shortcut for objects. It is a shortcut for information, and only in a very restricted, non-traversable sense even then. Think of it like two rooms that share a wall you cannot see through, cannot knock on, cannot pass a note across in any ordinary way. And yet the wiring behind that wall connects every switch in one room to every switch in the other instantly and completely. Nobody is walking between the rooms, but whatever happens on one side of that wall shows up, correlated on the other side, because the connection running behind it was never built for foot traffic. It was built for signal. That is roughly the register these island wormholes occupy. They carry entanglement, not passengers, and they let the radiation outside encode, in principle, everything sitting inside, without ever opening a door a person could walk through. Here is where the field splits. Physicists broadly agree that the math works. The calculation reproduces Page's curve. The numbers check out. The technique has been reproduced independently by multiple groups using different methods. That much is not in dispute. What is very much in dispute is what these wormholes physically represent. Once you stop treating them as a tool inside a computation and start asking what they would mean if you took them as literally true features of a real black hole's geometry. Some researchers argue they are telling you something deep and real about how spacetime is actually stitched together at the quantum level. Others argue they are a mathematical convenience, an artifact of how the calculation is structured, useful for getting the right answer without describing anything that is genuinely there in any physical sense. That disagreement matters because it marks the edge of what this breakthrough actually accomplished. The paradox looks mathematically dissolved, at least inside these controlled, simplified models, the same models built on Moldacina's ad's playground, rather than the messy, expanding universe you're sitting inside right now. Nobody yet has translated that dissolution into a clean physical story for an actual astrophysical black hole, the kind sitting at the center of a real galaxy radiating for real, with none of the tidy boundary conditions these calculations depend on. The equations balance. What they are describing in the world outside the chalkboard is still very much an open question. Go back to the equivalence principle for a moment, because everything in this chapter depends on taking it seriously one more time. General relativity has always insisted that a large enough black hole should not announce itself at the horizon. Falling through should feel like nothing at all. No alarms, no walls, no sudden jolt marking the boundary between out here and in there. You would cross into the interior the same way you would drift past any other patch of empty space gravity, smooth the whole way through, because that is what the equivalence principle has always demanded of any horizon, large enough that tidal forces stay gentle. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, ran a thought experiment that tested that promise severely. It is usually called the AMPS paradox after their initials, and it starts with an observer named Alice. Alice stays outside the black hole.
She does not fall in.
Instead, she waits, and she collects Hawking radiation as it streams out particle by particle, well past the page time, deep into the second half of the evaporation, where, as you now know, information is supposed to be escaping in scrambled but recoverable form. Alice takes one of those late radiation particles and checks something specific. Is it entangled with the earlier radiation that already escaped? If information really is coming out the way the island calculations demand, the answer must be yes. That particle needs to be tied to everything that left before it, part of the same slowly purifying cloud. But here's the second thing that same particle is required to be entangled with. As described earlier in the horizon-splitting picture from Hawking's original discovery, every particle of radiation is born paired with a partner particle falling inward across the horizon into the black hole's interior. That pairing is what allowed one twin to escape in the first place. So this particle needs to carry entanglement with its infalling partner too. And that is where the trap closes. Quantum mechanics has a rule called monogamy of entanglement, and it is not a suggestion, not a rough tendency, not something that bends under the right conditions. It is absolute. A particle that is maximally entangled with one partner cannot also be maximally entangled with a second separate partner. Zero room. Not 90% entangled with one and 10% with another. If the bond with one partner is complete, there is nothing left over to share with anybody else. The math simply forbids it, the same way the no-cloning theorem forbids 2 identical copies of an unknown quantum state existing at once, and for the same underlying reason. Entanglement is not a resource you can spend twice. Spend it fully on one connection, and every other connection has to come up empty. Think about what that means in practice, because the abstraction hides how strict this actually is. If 2 particles are entangled, you can picture them as sharing a single finite pool of correlation between them. Pour that pool entirely into one relationship, and there is nothing left to pour into a second. Try to force a third particle into the same intimacy, and quantum mechanics does not politely decline. It makes the configuration mathematically impossible. The same way you cannot have two different numbers both equal exactly 1. Now look at what Alice's radiation particle is being asked to do. It needs to be fully entangled with the old radiation outside, the cloud that already escaped, so that unitarity holds and information really is coming out. And it also needs to be fully entangled with its infalling partner at the horizon, the twin it was born with the instant Hawking radiation formed. Both relationships, at full strength, simultaneously. Monogamy says, pick one. Something must give. If you want to save unitarity, preserve the idea that information genuinely escapes, you have to break one of these entanglements, and the cheaper one to sacrifice is the link between the particle and its infalling partner at the horizon. But breaking that link is not free. Severing an entangled connection takes energy, real, calculable energy, and the amount required to sever every single one of these horizon connections, all at once, concentrated into an infinitesimally thin shell right at the boundary, turns out to be enormous. That concentrated energy is the firewall. A firewall is not a metaphor here. It is a wall of extreme energy sitting exactly where the horizon should be smooth and empty, and anything crossing it, Alice included, does not pass through discomfort or gradual heating. It meets a wall of radiation so intense that every bond holding her body together, atomic molecular, is torn apart instantly, thermalized before ever reaching the interior at all, not injured, not slowed down, converted to plasma in the time it takes to cross a boundary the equivalence principle swore would feel like nothing. Notice what that trade actually costs, because this is the part that should stop you. It saves unitarity by murdering the equivalence principle outright. The same principle Einstein called his happiest thought, the one that has sat underneath every prediction general relativity has ever made about falling bodies and curved space. A large black hole was supposed to be gentle at the horizon. That was the whole point of a horizon being just geometry, rather than a wall. The firewall says no. Actually, there is a wall, and it is the most violent one physics has ever proposed. And that leaves physicists standing at a standoff, forced to choose which foundation they are willing to give up: a horizon that behaves the way Einstein always said it must, or the quantum rule that information can never disappear. Neither side has produced a way to keep both intact. Not every physicist accepts the trade that firewalls demand. Samir Mathur, a string theorist, spent years constructing an alternative path out of the same trap. His solution does not force you to choose between unitarity and a smooth horizon. It removes the very piece both sides were fighting over. Consider the central insight. What if a true event horizon never forms at all? Not a horizon disguised, not a hidden firewall, but no sharp boundary anywhere in the geometry. And take it further. No true singularity, crushing everything down to a point. The two features that made this paradox possible, the one-way door and the infinite crush behind it, are argued to be absent in a real black hole. In their place, Mather proposes an object built directly from string theory's own ingredients. When enough matter collapses under gravity, it does not compress into emptiness wrapped around a point. It becomes an enormous, impossibly dense structure made of strings, the same fundamental strings used to build every particle in the universe. But here they are stretched and tangled and packed so densely that the entire structure extends to where the horizon would otherwise sit. Picture a ball of string, every strand stretched taut, woven through every other, layered so many times that the tangle behaves as one solid object. Its surface sits exactly where the black hole's boundary is supposed to be. That is a fuzzball, not empty space surrounded by a horizon with geometry alone inside. It is an actual object filling the space a horizon once sealed off, all the way through. Follow the collapse itself, step by step, because that is where this picture actually breaks from the classical one. In general relativity matter, falling inward keeps falling, past any point of no return, all the way down to a single point of zero size, and nothing in the equation stops it. In string theory, that same collapsing matter behaves completely differently once it gets small and dense enough for stringy effects to take over. Individual strings do not just sit passively inside the collapsing mass, waiting to be crushed along with everything else. They stretch. They tangle with neighboring strings. And crucially, string theory predicts that the more energy you pour into a string, the longer it grows, not the smaller it gets. Squeeze matter down far enough, and instead of continuing to shrink toward a point, it turns into a colossal, sprawling tangle of string spread out across a region the size the horizon would have been. The collapse does not run away to zero. It runs into a floor made of string. That single difference removes both broken pieces of the classical picture at once. No singularity, because the strings never finish collapsing to a point. The tangle simply gets denser and more complicated as more matter joins it, and no true horizon either, because a horizon is only a horizon if there is empty curved space sitting underneath it, funneling everything down to that hidden point. Take the point away, and the geometry never needs the funnel. The fuzzball's surface, fuzzy and structured at a level far below what any classical description could resolve, sits exactly where smooth spacetime used to promise you a clean, sealed edge. Now, see how this resolves the paradox, and notice how differently it gets there compared to the island formula you already walked through. The islands do not touch the horizon at all. They leave it standing sharp and absolute exactly where general relativity always put it, and instead reach backward through the interior with a gravitational contribution to entropy, smuggling information out through the geometry of a region nothing is supposed to escape from. Fuzzballs take the opposite route entirely. They do not smuggle anything past the horizon. They delete the horizon. If no true horizon exists, there is no sharp interior cut off from the universe in the first place. Information was never trapped behind an absolute boundary, because the boundary was never absolute. It rested in the structure of the fuzzball's surface all along, encoded in the kind of detail a smooth classical horizon would have erased. Nothing needs to tunnel out through Hawking radiation, carrying secret correlations. No island formula reaching back through the interior. The information was accessible from the surface the whole time, because the surface was never a horizon.
Where does this stand today?
It remains an active, mathematically serious research program, built on real calculations in string theory, not hand-waving. Detailed models of specific black hole configurations allow direct checks of the fuzzball picture against known results. But it is one picture among several competing with islands, complementarity, and firewalls, none of which have fully displaced each other. Nobody has produced the single settled answer the field has chased since Hawking's first calculation. Before the firewall reopened the fight, an idea attempted to settle it. Physicists call it black hole complementarity, and its central claim sounds like it should not be allowed to work at all. Information gets destroyed at the horizon. Information also survives, encoded in the radiation.
Both.
At the same time, not one answer waiting to be discovered correct, while the other proves wrong, but two full contradictory descriptions, each completely true, depending entirely on who you ask. Examine the two perspectives directly. The trick only becomes clear once both sides are visible. Stand outside the black hole, far from the horizon, patient enough to wait for complete evaporation. From out here, nothing crosses that boundary cleanly. Anything falling in smears across the horizon. Its information stretched thin, mixed into the surface, radiated back out over the black hole's remaining lifetime, scrambled but present. This is exactly the story the island calculations were built to support. From this vantage point, the interior never swallows anything. It stores it, badly, and releases it later. Now become the observer who falls in. Cross the horizon, and complementarity insists you feel nothing unusual. No wall, no smearing, no sense that your information has been peeled off and stored behind you. You drop straight through, as the equivalence principle has always promised, continuing toward the interior as if the horizon were never there. Here is why this is not a contradiction on its own terms. Be precise about the logic, because it is slippery. Complementarity does not claim both stories are true in some soft agree-to-disagree sense. It claims that no observer can ever occupy both positions at once and compare notes. The outside observer who waits for the radiation and reads the scrambled information back out can never also fall through the horizon to check the interior. And the observer who falls through and experiences nothing unusual can never climb back out to compare that with the smeared, radiated version outside. The two descriptions never meet inside a single frame of reference. Nature may tell two stories, because nobody is ever positioned to hear both at once. Consider an account of the same event told two different true ways, depending on where you stand when it happens. But here, the two tellers can never occupy the same spot to compare versions, not because of inconvenience, but because the geometry itself forbids it. As long as no observer can access both storylines, physics never gets caught contradicting itself. That is what made the firewall argument so damaging to this entire framework. AMPS did not need Alice to fall in and report back out. They only needed her to check, from outside, whether entanglement crossed the horizon, using radiation she had already collected, without occupying both vantage points simultaneously. That is exactly the loophole complementarity insisted was impossible. A way to test both stories, the smeared exterior and the smooth interior, from a single frame. If Alice can find the answer without complementarity's built-in excuse of "you can never check," then the whole scheme that let information be both destroyed and preserved stops protecting anyone from the contradiction it was designed to hide. Every step you have taken through this investigation, Van Ramsdonk tearing space-time apart, the wormholes stitched from entanglement, the islands reaching back into a black hole interior, every piece of it tells a story only about space. Distance, connection, geometry, all built from correlations between quantum systems sitting on a boundary. That fact raises a question carrying far more weight than most people recognize. If entanglement can construct space, what becomes of time? Here is the honest answer, stated without pretending it is more settled than it actually is. Holography, as far as anyone has shown mathematically, is a theory about space, not time. No ambiguity there. The entire framework, from T. Hooft's original conjecture through Mulder-Saner's correspondence to every island calculation that followed, describes how the contents of a spatial region get encoded on a spatial boundary. Time sits outside that story, running along in the background, doing whatever time does, with no one having derived it from entanglement the way distance was derived. That gap ought to feel strange. Everywhere else in this investigation, entanglement kept turning out to be the hidden mechanism beneath something people had assumed was basic. Distance turned out to be secretly built from correlation. The connectedness of two regions of spacetime turned out to be nothing but how entangled they were. So why would time, of all things, be exempt? Why would the one dimension holding cause before effect, the one direction physics insists never runs backward, sit untouched by the same logic that dissolved space into something derivative? Nobody has a clean answer, and that is exactly what unsettles the physicists working this problem today. Entanglement, causality, and the arrow of time all seem tangled together in ways nobody has managed to fully pull apart. You heard earlier how the growth of entanglement across a system drives entropy's rise, and entropy's rise gives time its arrow in the first place. So time and entanglement are clearly related somehow. But related is not the same as time being built from entanglement, the way space apparently is. Nobody has shown that causality itself, the requirement that causes precede effects, is a product of quantum correlation rather than a rule sitting underneath it untouched. Push the question further the way this investigation has pushed every other assumption. What if causality itself turns out to be merely an approximate pattern, something that holds reliably at the scales we experience, but is not a bedrock rule woven into the deepest layer of physics? What if, at the level where entanglement is truly fundamental, cause and effect are more like weather, a pattern reliable enough to build a life around, but not a law carved into the foundation the way physicists have always assumed? The physicists working this problem are honest about it. They do not know. Not as a hedge, not as false modesty, but as an accurate description of where the math currently stops. Whether time is fundamental, sitting at the bottom of reality the same way physicists once assumed space did, or whether it is emergent, built from something more basic, the way space now appears to be, or whether it is something stranger than either option, nobody has produced the calculation that settles it. Holography solved space. It left time exactly where it found it, ticking along, unexplained, waiting for whatever comes next. Here is the part of this investigation nobody gets to skip past comfortably. Everything you have heard so far, the bulk and the boundary, the wormholes stitched from entanglement, the islands reaching back through a black hole interior, every single piece of it was built and proven inside a mathematical playground called anti-de Sitter space. And our universe is not anti-de Sitter space. Not approximately, not in some limit where the difference washes out. It is a different shape entirely. State it plainly, because the physics community states it plainly too. Anti-de Sitter space has negative curvature, the saddle shape you heard about back when this framework was first introduced, a universe that stretches and curls in a way that makes a boundary sit at an infinite distance, always there, always reachable in the mathematical sense, never expanding or changing its basic character. Our universe does none of that. It has positive curvature and it is expanding. Not just expanding, but actually speeding up. Where ADS sits still, patient and static, letting theorists build entire calculations on the assumption that nothing about its basic shape changes. Our universe is doing something dynamic, restless, moving. Physicists call this kind of universe de Sitter space, essentially the opposite curvature from the ADS playground you have been sitting inside for most of this investigation. Where ADS bends inward like a saddle, de Sitter space bends outward. And where ADS gives you a boundary sitting patiently at spatial infinity, de Sitter gives you something stranger. Its boundary, if it has one worth talking about, sits at infinite future time rather than infinite distance. Not a wall far away in space, a wall far away in when. Sit with why this matters enormously, because it is not a footnote. It is close to the whole ballgame. The one holographic model that has actually been mathematically proven, checked, reproduced, used to derive the page curve and build the island formula and stitch wormholes out of entanglement, all of it lives in ADS. Every triumphant result from this entire investigation was won on a mathematical field that is not the one we are standing on. Maldaceno's correspondence is rigorous. It is also, as far as anyone has shown, a description of a universe that does not exist. So the search for alternatives has turned the field's attention exactly here. There is DS/CFT, an attempt to build the same kind of boundary duality, but for a de Sitter universe instead of an anti-de Sitter one. There is celestial holography, which tries something even stranger, defining the boundary not at some distant edge of space at all, but out at the far future, or along the paths light rays trace to infinity, redefining what boundary even means once you stop assuming space has to hold it. These are not fringe proposals. They are serious research programs, pursued by the same physicists who built the ADS results in the first place, precisely because everyone involved knows the current triumph does not yet describe home. Land on the honest state of things, because false comfort does not belong here. By the physics community's own admission, nobody has found a clean, rigorous, holographic description of a universe shaped like ours. Not yet. Everything you have learned about entanglement building space, about information surviving, evaporation, about gravity, emerging from a boundary theory with no gravity in it at all, stands on solid ground in a universe that is not the one you're sitting in right now. Whether it translates is an open question, one of the largest this entire field is currently chasing. This investigation needs one more piece of technical machinery before it can go further, the piece that lets physicists calculate instead of just describe. It is called the Ryu-Takayanagi formula, and it does something that sounds almost too simple to carry the weight it does. It connects entanglement entropy directly to geometry. Without the equation, here is the meaning. Take the boundary theory, the flat, gravity-free quantum system living one dimension down. Pick a region of it. Measure how entangled that region is with the rest of the boundary. Ryu and Takayanagi showed that this number, the entanglement entropy of that patch, corresponds exactly to the area of a specific surface curving through the bulk, the smallest surface you could draw that has the same edge as your chosen region. Find that minimal surface, measure its area, and you have the entropy. No approximation, just a direct dictionary entry between a quantum information quantity on the boundary and a geometric quantity in the bulk. Consider what that actually gives you. It is a strange kind of power. You can read geometric distance directly off of entanglement. To know how far apart 2 points are inside the bulk universe, you do not reach for a ruler. You measure how entangled the corresponding regions are on the boundary, and the geometry emerges from that measurement. This is the same idea Van Ramsdonk's thought experiment gestured at distance as a function of entanglement, except now it comes with an actual formula attached one physicists use constantly in real calculations, to move back and forth between the two sides of the correspondence. That formula led somewhere nobody expected. Physicists started asking what happens if you take a small piece of the boundary and erase it. Delete some of the quantum information sitting there. and see what you lose in the bulk picture. The answer, in a wide range of cases, was less than you would think. The same piece of bulk geometry, the same object, the same region of space, turned out to be encoded redundantly across many different overlapping patches of the boundary. Lose one patch, and the geometry it described was still reconstructible from the information sitting elsewhere. That is the signature of an error-correcting code. Think of a document backed up in fragments scattered across a dozen separate drives, deliberately structured so that no single drive holds the whole thing. But losing any few of them still leaves you able to rebuild the entire file from what remains. Nobody engineered spacetime this way on purpose. Nobody sat down and designed a redundancy scheme. But that is exactly the behavior the Ryu-Takayanagi formula, pushed far enough, kept revealing. Bulk information was not sitting at one address on the boundary. It was smeared across many addresses at once, overdetermined, resistant to damage. The implication is worth stating plainly, because it reframes something this investigation has been circling since the opening chapters on entropy and the horizon. Spacetime on this picture does not behave like a fragile, continuous backdrop that tears the moment something goes wrong with it. It behaves like a self-healing information system, one where individual pieces of the underlying quantum data can go missing without the geometry itself collapsing. That is a very different picture of what space fundamentally is, and it is one more piece of evidence, sitting alongside everything Van Ramsdonk and Maldacena and the island calculations have already shown you. Whatever spacetime actually is at the deepest level, it looks a lot less like a stage and a lot more like a code. Everything in this investigation so far has lived inside mathematics. Bulk and boundary, islands and wormholes, error-correcting codes stitched from entanglement, all of it worked out on paper, checked against other paper, never once touched by a measurement taken in the real world. That is not a criticism. Some ideas in physics simply sit too far from any instrument we can build, but a handful of physicists decided the holographic principle did not have to stay there, and they went looking for a way to drag one small piece of it down into something a detector could actually catch. The logic they built the test on goes like this. Ordinary quantum field theory treats every possible state of a system as sitting in its own separate slot, mathematically perpendicular to every other slot, the way two directions on a map never overlap. Holography, if it is really imposing a hard limit on how much information a region of space can hold, suggests something different. That once you try to pack in more states than the boundary can actually support, those slots stop being perfectly separate. They start to overlap, just slightly, crowding into each other because there simply is not room for all of them to stay distinct. And if that is true, it should show up as a specific physical effect. High-energy particles traveling across enormous distances should occasionally behave as if they are not quite in the state you thought they were in, because the state itself was never fully separate from its neighbors to begin with. That is a strange thing to search for, but there is an instrument built for exactly this kind of patience, sitting at the bottom of the world. Picture this: a detector made from a cubic kilometer of solid Antarctic ice, threaded with strings of light sensors sunk deep beneath the surface, watching for the faint flash that happens when a neutrino, one of the most weakly interacting particles known, strikes a molecule in all that ice. The instrument is called Ice Cube, and the name is almost literal. Drill more than 80 holes straight down into the ice sheet at the South Pole, each one over a mile deep, and lower a long string of basketball-sized glass spheres into every one of them before the water refreezes around them and locks them in place forever. Thousands of these spheres, arranged like beads on dozens of vertical strings, turn an entire cubic kilometer of frozen water into a single silent eye pointed at the universe. Here is why ice, specifically. Ice is transparent enough that a faint flash of light can travel through it for 100 meters or more before fading out, which means a handful of sensors spaced far apart can still catch a signal that would be invisible in murkier material. It is also motionless cheap to work with, once it is already sitting there in a kilometers thick sheet, and it sits in one of the only places on Earth quiet enough, dark enough, and free enough of interference to let a whisper-faint signal survive to the sensors at all. Neutrinos pour through the Earth constantly, from the sun, from deep space, mostly ignoring everything in their path the way a bullet ignores fog. Once in a great while, one does not ignore it, striking a water molecule and producing a brief cone of blue light called Cherenkov radiation. The glass spheres exist for exactly one purpose: to notice that cone of light, catch it flickering past in the dark, and record precisely when and where it happened. The specific prediction this holographic idea produces is this: if quantum states really do start overlapping once you push them far enough, then think of each possible particle state as a direction you could point in a very high-dimensional space. Ordinarily, you can only fit so many directions that all point perfectly away from each other before you run out of room and they start to lean into one another. Holography claims nature runs into exactly this kind of overcrowding once you try to pack more physical states into a region than the boundary can support. If that lean into each other effect is real, it should surface as a small specific rate of neutrinos briefly slipping from one flavor into another mid-flight, more often for the highest energy neutrinos and the longest journeys, in a way ordinary quantum field theory, with its cleanly separated states, never predicts at all. Not a small correction sitting quietly in the noise, a cutoff, a point on the chart where the numbers should visibly, unmistakably drop. The physicists went to the actual ice cube data and looked for exactly that drop. The honest result, without dressing it up as more than it is this: the count of detected neutrinos does fall off close to where the prediction says it should, tapering out sharply, right around the highest energies the theory flagged as suspect. But the detector itself loses sensitivity at almost exactly that same energy, for the mundane reason that fewer and fewer high-energy neutrinos ever reach the ice in the first place, no matter what physics governs them along the way. Which means nobody can currently tell whether the neutrinos genuinely vanished the way holography predicts, or whether ice cubes simply ran out of particles to see it all. It's eye going dim for reasons that have nothing to do with quantum overcrowding whatsoever. That is not a triumph, and it is not a failure either. It is an actual real attempt to test one of the strangest ideas in modern physics, run against real data collected at the bottom of the planet, and the honest answer it returned was suggestive, not conclusive. The cutoff lines up. Nobody can yet say why. Sometimes that is the most physics can give you, at least for now. Take the same bound that has governed this entire investigation, the limit on how much information a region can hold before it collapses into a black hole, and stop applying it to stars and horizons for a moment. Apply it to everything instead. The whole observable universe, treated as a single region with a boundary of its own. Before you can see why anyone would try that, you need to grasp the problem it is trying to fix. This one did not start with black holes at all. It started with empty space itself refusing to behave. Quantum field theory says the vacuum is not nothing. You have heard this already, the flickering pairs popping in and out of existence everywhere, constantly. Add up the energy of all that flickering across every scale quantum theory claims to know about, and you get a number for how much energy empty space should carry. Compare that number to what telescopes actually measure, the real vacuum energy driving the universe's expansion, and the two do not just disagree. They disagree by a margin so large it barely counts as an error anymore. It is closer to two completely different universes described by the same equation, one of them real, the other a wild overestimate nobody has ever fully tamed. Physicists have a name for this: the cosmological constant problem. It has sat there unresolved for decades. Consider the scale of that mismatch, because disagree undersells it badly. This is not a calculation that overshoots by a little, the way a weather forecast might miss tomorrow's temperature by a few degrees. Quantum field theory predicts a vacuum energy so much larger than what we actually observe that the gap dwarfs almost every other number in physics. Picture trying to measure the width of a single hair and getting an answer larger than the distance across the observable universe. That is roughly the flavor of the error hiding inside this calculation. No other prediction in the history of physics has ever missed by a margin anywhere close to this large, while the rest of the theory around it keeps working beautifully. That contradiction alone is enough to make physicists suspect something basic about how they are counting vacuum energy has to be wrong. Here is the holographic fix, and it works the same way the bound has worked every other time you have seen it in this investigation. Do not let a region hold more energy than a black hole of that same size could hold.
Cap it?
Take the entire universe, draw its boundary at the cosmic horizon, the furthest edge from which light could ever reach us, and say the total energy inside cannot exceed whatever a black hole stretching out that far would carry. Once you impose that ceiling instead of trusting the raw quantum field theory calculation, the absurd number shrinks down to something far closer to what we actually observe. The fix is not a better calculation of the vacuum. It is a boundary condition borrowed directly from black hole thermodynamics, applied at the largest scale anyone has ever tried to apply it. Here is what that produces. It is not a fixed number anymore. It is a moving target. The cosmic horizon is not static. As the universe expands, that horizon shifts. And if the energy ceiling is genuinely tied to the horizon's size, then what we call dark energy is not a fixed constant, sitting quietly in Einstein's equations. It is dynamic, evolving alongside the changing size of the boundary itself. Not a fixed number nature happened to pick. A number that answers to geometry, recalculated as the universe's edge moves. But here is where it gets uncomfortable. If dark energy tracks the horizon, rather than sitting fixed the universe's entire future, depends on which boundary this framework says actually matters, because there is more than one candidate horizon to choose from, and different choices produce genuinely different fates. Tie the bound to the current cosmic horizon, the one we can actually measure right now, and you get a universe that simply keeps expanding forever. Galaxies drifting apart at a rate that gradually slows into something calm and cold. Stars burn out, galaxies scatter, the night sky empties, one light source at a time, but nothing ever tears. It is a quiet ending, and a distant one. Tie the bound to a different horizon, and the outcome changes completely. In some versions, the energy density does not keep dropping toward nothing. It levels off, settling into a fixed value and holding there. A universe that reaches a kind of permanent twilight and simply stays there, neither expanding into oblivion nor collapsing back on itself. Stable, but not comfortable. A universe frozen in place at the very edge of nothing. And then there is the version nobody wants to be living inside. Tie the bound to a future horizon instead of the present one, and the dark energy density does not level off or fade. It climbs. It keeps climbing, feeding on the geometry of a boundary that keeps receding ahead of it, until the expansion itself outruns gravity everywhere at once. Galaxies get torn from their clusters first, then solar systems come apart, then planets. Then at the very end, the bonds holding atoms together give way too. Physicists call this the Big Rip, and it is exactly what it sounds like. Not a fade to black, but a shredding, running to completion in a finite amount of time rather than trailing off into eternity. 3 different choices of boundary, 3 completely different endings for everything that exists, and nothing in the mathematics currently tells you which one is real. Nobody has settled which boundary is the right one to use. That is not a footnote here. It is the whole stakes. The same principle that told you a black hole's information lives on its surface might be quietly writing the ending of everything. Widen the lens now, because everything you have walked through so far, the islands, the wormholes stitched from entanglement, the boundary bound capping the universe's own dark energy, all of it points at the same uncomfortable suggestion. It is time to look at that suggestion directly instead of sideways. Physicists have a phrase for it, and it is older than most of the results in this investigation. It from bit, the idea that the physical world, matter, energy, the 4 forces, the whole apparent stage of reality, might all be secondary features sitting on top of something more basic, information. Not information as a description of things that are real. Information as the thing that is actually real, with matter and energy showing up
The
after.
luminous heart of
way
the
a shadow
star-forming
shows up
region
after you put an
bathes
object in
this
front of the
icy
light.
moon in a warm
Think
glow.
about a novel for a second. Not what is printed on its pages, but what the novel actually is. The story, the characters, the sequence of events, none of that lives in the ink. It lives in the arrangement, the pattern, the information the ink happens to carry. Print that same story in a different font, on different paper, in a different language even, and the novel survives every one of those changes intact, because the paper and the ink were never the point. They were one way among many possible ways of displaying something that existed independently of its display. That is the reframe this entire investigation has been building toward, chapter by chapter, without ever quite naming it outright until now. Space built from entanglement, the way Van Ramsdonk's thought experiment tore 2 regions apart the instant their correlations disappeared. Gravity, emerging from a boundary theory that never had gravity written into it in the first place. The way waves emerge from deeper than anything physical. Here is where physicists split, and it is worth naming the split honestly, rather than resolving it for them. Some researchers treat this as the natural, almost inevitable conclusion of 30 years of results, from Bekenstein's entropy bound, through Maldaceno's correspondence, through the Ryu-Takayanagi formula's error-correcting geometry. To this camp, it from bit is not philosophy dressed up as physics. It is what the math has been telling everyone the entire time, and the only surprising thing is how long it took the field to say it plainly. Others push back hard, and not out of stubbornness.
Here, at the edge of the Lagoon Nebula, we see the very beginnings of creation.
Every version of the Ryu-Takayanagi formula lives inside De Sitter space, a universe that is not ours. Extrapolate from a proven result in a toy universe to a sweeping claim about the nature of all reality. And you have quietly swapped a calculation for a philosophy dressed in the same equations that earned trust doing something much narrower. Neither side has a knockout argument, and that is the honest place to leave it. This is not a settled question, and the people doing the actual math today, the ones building the next island calculation or the next boundary theory, disagree with each other about what their own results mean once you step back far enough to ask the biggest version of the question. The equations keep working. What they are ultimately made of is still being argued over right now by the very people who wrote them down. Pull back now and look at the whole case file spread out in front of you, because that's what this has been the entire time. Not a single mystery with a single answer waiting at the end, but a set of overlapping wounds, some of them closed, most of them still open. And let's name exactly which is which before this investigation goes any further. Here's what hasn't been settled, but bluntly. There's no accepted microscopic mechanism for what actually happens inside a real astrophysical black hole, the kind sitting at the center of a galaxy formed from a collapsing star, radiating for real over cosmic timescales, instead of inside a chalkboard model built for convenience. No holographic picture of our actual universe exists either. The expanding, positively curved one you're sitting inside right now, only of the static, saddle-shaped one Maldaceno's correspondence was built on, and firewalls remain unresolved. Physicists split between sacrificing the equivalence principle and sacrificing unitarity, exactly where the amps argument left them. Now say plainly what has been settled, because burying the real progress under the remaining uncertainty would be dishonest. The logical contradiction at the center of the original paradox, information either destroyed or duplicated, either eaten or leaked, is widely considered dissolved, not guessed at. Dissolved mathematically inside controlled simplified models, the island formula bending pages curve exactly where unitarity demanded it. Bend the Ryu-Takayanagi dictionary reading geometry straight off of entanglement. Wormhole-like structures carrying that information without breaking a single rule quantum mechanics insists on. That's real. Multiple groups reproduced it independently, using different methods, and got the same answer. But settling a contradiction inside a model isn't the same as explaining a black hole. That's the honest gap, and it's the one this whole investigation keeps circling back to. Translating a dissolved paradox it adds into a story about a real black hole, the one with actual matter falling into it, actual Hawking radiation streaming out over billions of years, actual spacetime that isn't saddle-shaped or static. Nobody has done that yet. The math works, but what it's describing out here in the universe you actually live in remains an open question that the field's own leading voices refuse to paper over. Name the disagreement plainly too, because pretending physicists have quietly converged on one interpretation would be its own kind of dishonesty.
Orbiting this
One
massive
camp
gas
treats the
giant,
islands and wormholes
the
as
rings
literal
stretch
geometry,
across millions
real
of
stitching of space-time. The other sees the same calculation as a computational device, useful for getting the right entropy out the other end, without describing anything that's genuinely there. Both camps are looking at identical equations, and neither has produced the argument that forces the other to concede. Sit with that discomfort deliberately, because it's the truest thing to say about where this field actually stands. This is an area of physics where some of the sharpest minds alive, the ones who wrote the island formula, first proposed ER equals EPR, and are running high school's data against a decades-old speculative bound, freely admit they're still building the map while walking on it, not pretending to have arrived, still walking. So look at the room you're sitting in right now, the walls, the light, sense of depth from you to the far corner. Everything this investigation has walked through says that description. The one your senses give you for free might not be the deepest one available. Somewhere on some boundary none of us can see in a language built out of quantum bits rather than distance and depth. There may be an equivalent description doing all the same work, and both descriptions might be equally fully real. Refuse the easy comfort here, because it's not actually on offer. This isn't a simulation, not in the cheap sense that phrase usually carries, some programmer's world running on hidden hardware somewhere outside it. It's stranger than that, an equivalence, two descriptions of one reality, neither one or real on the other. The bulk and the boundary each complete on their own terms, each able to answer every question the other can, with nothing left over that only one side knows. Go back to the person who fell into the black hole at the start of all this. Remember them. They crossed the horizon feeling nothing, the way the equivalence principle always promised they would, and on the outside decades became centuries.
This stunning,
while the black hole
barred
thinned
spiral
itself
galaxy
down.
is cradled within a
You
massive
asked at the
nebula.
very beginning where their information went. You now have an answer, or at least the shape of one. It did not vanish behind that horizon. According to everything this investigation has walked through, it was never sealed away in the first place. Not really. It was written into the
We are
correlation
witnessing the
between every
cosmic
particle
dance of a
radiation that
massive
ever
galaxy
left,
cluster,
smeared across a
a
boundary,
spectacle of
redundant,
unimaginable scale
overdetermined,
and beauty.
recoverable in principle by anything patient enough and precise enough to read it back. That person is gone in every practical sense. Nobody is reconstructing them from a puff of photons scattered across light years of empty space. But gone and erased are not the same word, and this entire investigation has been an argument for keeping those two words very far apart. The universe, as far as physicists can currently tell, does not forget. It just gets extremely good at hiding what it remembers. Picture, one more time, a black hole finishing its evaporation. Billions of years of collapse and radiation, thinning down to a final hiss, and then nothing left but photons scattered across an enormous volume of space, carrying, somewhere in their correlations, everything that ever fell in. That hiss is not silence. It is the sound, if you could hear it, of a record closing out, of a book that looked burned to ash, somehow still legible, if you knew how to read fire. Physicists are arguing about that hiss right now, tonight, in papers being written while you listen to this, about what those wormholes really are, whether time emerges the way space does, and which boundary governs the universe's fate. Sit with what it means to be a person made of information, sitting inside a description that might itself be secondary. You are, on this picture, not a fixed object moving through a fixed stage. You might be closer to a pattern, stable for now, entangled with everything nearby, readable in principle from someplace you will never visit, on a surface you will never touch.
That should feel unsettling, and it is fine to let it.
Sitting with the discomfort is more honest than resolving it early. The room around you is real. The depth you feel is real, but real does not have to mean fundamental. And this entire investigation has been a long argument for how much distance can exist between those two words once you look closely enough at anything. That argument isn't finished, not even close. And that's exactly why this isn't the end of the case file. It's where this one closes for now, with the paradox mathematically quiet but physically unresolved, waiting for whoever picks up the next thread.